All right, hello and welcome to Mr. Brown Science class for today. Today we're going to be kind of investigating a little bit more into compounds. We've already talked about elements and elements off the periodic table and how they, all have their own identities and specific properties. So today we're going to look at compounds, which is kind of the next evolution. So when we start taking elements and building different things with them, I always like to think of elements as single Lego bricks, and compounds we're starting to look at these things as Lego sets. So they can be simple Lego sets, but you're still putting a couple of these different elements together. So today's lesson objectives, we're going to determine what is a compound and we're going to identify its properties. We're also going to be looking at chemical formulas, and we'll be taking that idea and moving on with it in a later class. I do have my information there. If you ever need to contact me, feel free to do so through my email or my phone extension if you need to get a hold of me. All right, so we'll start it off. Compounds. As far as what a compound is, it's a pure substance made of more than one type of element. So you have at least two different types of elements that are chemically bound. Okay, and this is on the molecular level. We have these bonds, ionic covalent hydrogen bonds, that are taking place and hooking these two different types or more of elements together and forming a new substance. They're always present in a fixed proportion. In other words, you always have the same amount to make a specific compound. Just like your name has the same letters in it, you can only spell it with the correct number of letters. These compounds can only be created with the correct number of elements present. So why do compounds exist? The whole reason behind a compound is to form a stable structure. So elements, as we've learned already, can be extremely reactive. So I have here listed some of the alkali earth metals, potassium, calcium, looking at some of those highly reactive elements that will react with even the water in the air around you, so you can't even hold them in your hand without them reacting. We also have halogens here like chlorine gas and fluorine. These things are very readily willing to react, so they form compounds with other elements to give themselves a little bit more of a stable structure. Don't think of them as living. It's just the world functions a lot better when things are kind of balanced and stable. Compounds are able to take reactive elements and combine them, into these stable structures without, much issue. Sometimes there can be some outward presence of reaction, but for the most part, it can happen pretty readily. I do have a list here of some examples of common compounds that you've probably come into contact with or have heard of. So salt, which is NaCl, which is sodium chloride. Water, H2O. We've all heard of water, I hope. Hydrogen or hydrochloric acid, so HCl, so hydrogen and chlorine. Carbon dioxide, CO2, carbon and oxygen. And ammonia, which is used as a cleaning product, which is nitrogen and hydrogen. And we'll come back and look at these chemical formulas here and kind of determine what all those things mean. But as of right now, we'll just look at them as common compounds. Before we can talk about a compound, we have to get a little bit of terminology. So we also use the word molecule quite a bit when we talk about compounds. So a molecule is two or more atoms chemically bound, and its smallest particle is called a molecule. So an example, if we have a compound of water, a single molecule of water is one oxygen and two hydrogen atoms bound together. If you took a single drop of water, or a glass of water, you would have countless molecules of water present. So a single grouping of one oxygen and two hydrogen makes one water molecule. Oops. As far as all molecules go, they share properties of its major compound. A drop of water shares the same properties as a glass of water, as a lake, as a a single molecule. They're all going to be the same. The properties are all the same. Now there's going to be stuff mixed in if there's a lake. So yeah, there's going to be, the stereotypical argument of, well, what about this and what about that? But as far as the water specifically goes, all the properties will be the same no matter how much you have. Because of this, compounds made of molecules that share the same properties, they're known as pure substances. Okay, once you are able to, look over the fact that there's going to be other stuff dissolved with it. Some other properties of compounds, they have their own unique properties. They don't retain the properties of the elements that make them up. And these properties can vary greatly from the elements that do make them up. So that's the really weird part about compounds, is that they don't look the same as the elements that are in them. So I have two examples here. Salt, which is NaCl, which is sodium and chlorine, which is necessary for life and delicious on French fries. You need to have sodium in your diet for necessary life processes for osmosis to take place. But if you have these two elements by themselves, sodium, which is a metal and it reacts violently with water, and then you have chlorine, which is a poisonous, gas usually that's used to kill bacteria in, say, like a swimming pool. Those two violently reactive substances or poisonous substances come together to make something that you literally season your French fries with and you eat and need on a daily basis. Another example is CO2. CO2 is found in a car exhaust. It too is poisonous, but it comes from carbon, which is pretty much what most of your body is made out of, and oxygen, which you need to life. So two things that by themselves are relatively, they're harmless, they're necessary for life, come together to make something that could kill you. So kind of the opposite of the example above. And this is very common in the world of compounds. You can break compounds down, and that's we're got to look at a couple methods. But to separate the compounds, you can break it down into the elements that make it up. Heat and electricity are what are often used. This process is called chemical decomposition. So an example that I have here is hydrolysis and thermal decomposition. So hydrolysis, looking at the Latin there, so hydro means water and lysis means to break. So you're breaking down water. Thermal composition would be using heat to break these compounds apart. Okay, so you can break these compounds down, where when we talked about elements, you can't break them down any further. So compounds can be broken back into their constituent parts. So the last part I'd like to talk about is that of chemical formulas. Chemical formulas are really important when it comes to chemistry. There's a lot of chemicals out there, and because of that, we need to identify them by essentially a name and a structure of how to, determine what these substances are. So a chemical formula is a combination of chemical symbols. So each element has its own symbol, and from there you can, take those symbols and build these formulas. Each chemical formula uses a symbol of the element present, and then it also uses numbers which are called subscripts. And we'll get into those in a little bit, but you've seen them written before, especially if you've seen like H2O. It's that little 2 that's the subscript. Okay, so the symbol tells you what element you're dealing with. So if I have H, as far as water goes, you have a little letter H, and then the subscript would be the number of how many of those elements are present in the actual chemical formula. So subscript, where it comes from, sub meaning writing, script meaning, sub meaning under, and script meaning writing. So it's underwriting essentially. That's why you see the little number at the bottom of the letters in the chemical formula. If there is no number present, it's just assumed that you have one of that element in existence or in that chemical formula. So I have a couple examples here. So I have water, which is H2O, and the H would be hydrogen. So I have it listed here, broken down. So hydrogen, okay? And then as far as the little 2 goes, right here, that little 2 means that it has a subscript of 2. So for every molecule of water, you have 2 elements of hydrogen. Notice there's no little number next to the O, so it's assumed that there's one of them. So we have one oxygen. Okay, glucose, which is sugar, it's essentially what plants use as storage, but what we eat and burn to make energy in our bodies, is C6H12O6. So we have C, which is carbon, and then a little 6, which means there's 6 of them. H, which is hydrogen, so we have hydrogen listed and 12 of them. And lastly, O, which is oxygen, and we have 6 of them based on the subscript. Okay. So as far as from here, what we're going to be doing is looking at these formulas in a little bit more detail later on. Okay, thanks for listening into the lesson, and we'll see you next time.